An example, we are given differential equation. Well, it's p of t. P is a function of t, but it's d dt, the derivative with respect to time of performance as a function of time, is equal to a constant k times m, where m is a constant. It's actually the maximum performance level minus p, which is a function of time. Okay, maximum would be the maximum you could do on, let's say, a test, 100%. So that's going to be constant. See, I want you to notice that both k and m are both constants. So if we ever want to figure out what those guys are, we're going to have some initial conditions. But let's see what else they tell us here. They want us to find two things. Part A, solution function. So the solution to this differential equation would be the function p of t. And in part B, they want us to find the limit. And the limit they want is the limit for the maximum performance. So they want, if you have infinite amount of time, I shouldn't say that, I should say if you had infinite amount of time, what limit will that give you as far as your maximum performance, as far as your performance level? P is performance level. Okay, let's do part A. First, we notice that this is a separable equation, and that's great because we really haven't seen much other than separable equations in the differential equation section. So we're going to separate it, and when we do, we'll end up, we won't use a t like p of t anymore, we'll just call it t. So we separate it and get 1 over m, maximum performance level, minus p, that's performance at time t, dp equals, we'll leave the k over on this side as the other function, dt. Now we'll take the integral of each side. And I like the p because that's performance level. That's my only variable. P is a constant, k is a constant. So I like the p to be positive. So I'm going to pull a negative sign out in the front and make this integral of 1 over p minus m dp equals, I could pull the k out, and this is the integral of 1 dt. Okay, taking the integral, we get the natural log of the absolute value. Remember, m is a constant, it's just a number, of p minus this constant m. Don't forget the negative sign in the front. And that's going to be equal to k times t plus the constant c. Now I want to get rid of the natural log because I'm trying to isolate p. So I'll just multiply both sides by -1. Move the negative sign over. You get k times t minus c. And now I'm going to have e on both sides. E to this side equals e to this side. Okay, now the e and the natural log cancel one another, and I get the absolute value of p minus m equals, I can break this apart, just a moment. I can break apart this e to the a plus b, because that's e to the a times e to the b, using the rules of exponents. So we have e to the k times t times e to the minus c. Oh, you know, I forgot to make this dude negative. The kt has to be negative also. Okay. Now, I want to get rid of the absolute value, and I can do that by naming, I'm going to say, a trick that we learned in class. I'm going to say, let this new constant I'm introducing, a, equal plus or minus e to the negative c. Now, because I said plus or minus, it's going to not only replace e to the negative c, it's going to replace, let's see, it'll get rid of the absolute value bars. So this is p minus m equals a times e to the negative k times t. Alright, now just move the m to the other side, and we got our function m equals p equals m plus a times e to the negative kt. And that, I'll put a box around that because that's the answer to part A. That is the function p of t. It's a function of time, and it is the solution to the differential equation. Now we go to part B, where they ask about the limit. And here we're going to assume something just from logic, that the performance level, which is what we call P, performance level, let's see, performance level P is going to be 0 when time studying or time working is 0. And that gives us actually an initial condition. Initial condition, which is the ordered pair. Instead of xy, we'll say TP, because P is a function of time, is 0, 0. And that initial condition will help us find a constant. So we're going to substitute 0, 0 into the P equation. Alright? And that will give us P of 0 equals m plus a times e to the 0. But of course P of 0, that's the y-coordinate in the ordered pair, that's just equal to 0. So we've got 0 equals m plus a, because e to the 0 is 1. But of course, if you just move things around, that just tells us that the constant a is equal to negative the constant m. Okay, so we're going to take this guy and refine him, this equation for P, and we're going to write it as P is a function of time is equal to m, and then we're going to say plus, let's see, minus, instead of putting plus a, we're going to put minus m, because that's what a is equal to, times e to the negative kt. And I put a little cloud around that because that's our new refined equation. It has only one unknown variable in it, it's m. Okay, so now we're going to finally answer the question where they're asked about the limit. The limit as the dependent variable t, time t, gets huge. It goes to infinity. So the infinite amount of time that you spend training, so the limit of the performance, the limit as time goes to infinity is the limit as t approaches infinity of the function p of t equals m minus m times e to the negative infinity, which is m minus m times 1 over e to the infinity, which is m minus m times 0, so it is equal to m. Thus, we have max, what was the value m? It is the level of a max level of performance P, which is m, when time t gets very large. And that makes all the sense in the world.